Okay, so I want to wrap up this unit by going over a heaping helping of heap terms and doing some review to help put everything in context for the lab. Okay, so what is a heap? Well, there are dictionary definitions of what a heap is. And what's a heaping helping? We'll look at both. So a heap is a pile, like this pile of clothes. So heaping helping is a kind of common phrase for a giant pile of things. So we'll look at a huge pile of the terms related to heaps. Okay, so first off, it's important to note that we've been focused on a binary heap. There are other types of heaps. So the binary heap uses a binary tree. The Fibonacci heap uses a slightly different structure and has better amortized time. So kind of the average time of repeated operations, particularly the insert, is better on the Fibonacci heap. There are also a bunch of other heaps. So Wikipedia has a whole article on just the Fibonacci heap, and under the general term heap, they list a bunch of different variants of heaps and show their different time complexities. Okay, but heaps are not just about binary data structures or data structures that store data. Another use of the term heap is for a large pool of dynamically allocated memory. So by that, I mean the memory that you end up getting when a program is running. It's dynamic. It changes over the course of the program. And at least in Java, when you use the keyword new, that's about allocating memory from this thing called the heap. So typically when you talk about how a programming language like Java uses computer memory, there are kind of two different major categories of memory, the heap and the runtime stack. And these have slightly different trade-offs to the way they manage memory and slightly different advantages. Those topics are covered in other courses. So the runtime stack itself actually acts like the data structure stack that we've already talked about. But what's kind of counterintuitive is that the heap may not actually be using a heap data structure. Okay. The important takeaway here is that sometimes in computer science you use heaps referred to when people are talking about the way computers' memory is organized, and other times you hear the word heap in the context of the way data is organized in the computer's memory. It's that latter one, the organization of data, that we will be talking about. Okay, so in this class we're focused on just binary heaps, so a very, very specific type of heap. So I wanted to do a quick review of a couple of operations and talk about some kind of conflicting terminology about these operations. So earlier we looked at some pseudocode for a heap insert. So I just wanted to review this. So there were a couple of different operations: creating a node, enforcing the shape property, and then we talked about all the stuff that was related to enforcing the order property. It turns out that these things for enforcing the order property are oftentimes useful in two different ways. They can be useful if you're inserting or removing something from the heap. They can also be useful if you're changing the priority of a particular item. So oftentimes this component is abstracted out so it can be used for both purposes, for inserting and for adjusting priority. Okay? The same is true with the corresponding element of the extract process. So just to back up for a second, in the insert process, it's all about going up the tree. So we'll start at the new leaf at the bottom of the tree and it'll proceed up the tree. For the remove process, it's all about taking away the root, replacing the root node with what was the end of the tree, and then progressing down the tree. So these kind of have natural directions associated with them. There are a bunch of different terms that can be used in slightly different places that oftentimes represent the same concept. So in this course, we're utilizing a zybook. In the class, we're using Java, and Java already supplies its own priority queue. There are other common definitions like Wikipedia and the Introduction to Algorithms book by Corman et al. And all of these have slightly different uses of terminology. So I want to take a quick look through a few of those. Wikipedia's definition of a binary heap defines the major operations to be insert and extract. But it also indicates the common names for the process that just takes care of moving a node into the proper place on the insert or the remove. So that would be just those components that did the loop that we already looked at. So the common names are bubble up, percolate up, sift up, trickle up, swim up, heapify up, and cascade up for the process of taking a node that's at the bottom of the tree and moving it upward to the proper location. There's a corresponding set of names for the opposite when we remove a node and have to take a value and put it at the root and move it down to the proper place. So common names are bubble down, percolate down, sift down, sink down, trickle down, heapify down, cascade down, extract min, extract max, or simply heapify. The Corman book also has names for just these components. So by the way, all of those names, the bubble up, bubble down, percolate down, those are all about just the step of maintaining the order property. The Corman book that's our recommended reading also refers to this process of moving something down the tree with the term heapify. So heapify or heapify down. Okay, so lots of terms and they're used in different places. Okay, so I want to break these down into a couple of different categories and just put them on in context really quickly. So they're external operations. So that's the things that someone who's using a priority queue will want the priority queue to do. Mainly, there are two major concepts I'm going to focus on, the idea of adding data to it and removing data from it. So adding data to it is usually referred to as an insert operation. So Wikipedia and Zybooks refer to it as insert, so does our Corman text, and in our lab we refer to it as an insert. Java's priority queues will refer to it as adding something. There's the corresponding concept of getting the best value, which is removing it. In many places that's referred to as an extract. So it's referred to as extract max and a max heap. We'll be dealing with a min heap, so in our lab it's extract min. The Zybooks refers to it as remove when they're talking about a heap, and pop when they're talking about the concept of a priority queue that may be implemented with a heap. The Java class refers to it as a poll, P-O-L-L. Okay, so those are the external operations. Someone who wants to use a priority queue probably mainly cares about adding things to it and removing things from it. There are also some internal operations that are used to maintain the priority queue. Okay, so one of the internal operations is about moving values up the tree into the right place. So that would be enforcing the order property, or the concept of increasing the priority of something. So this idea of maintaining the order property can be used in two different ways. It can be used both as part of the insert process, and also if you've got an adaptable priority queue where you can change priorities after something's already been added to a queue, you can use this exact same approach to adjust the position after the priority's been changed. So this goes by a lot of different names: percolate up, bubble up. In the Corman book, it's a max heap. So you can kind of think of it as increasing the priority as it moves up the tree. In our case, we're dealing with a min heap. So in our lab, we'll refer to it as a decrease. Java priority queues, this isn't publicly visible. But if you dig through the source code, they refer to it as sifting up. The complementary concept is enforcing the order property after data has been removed or after you're decreasing the priority. So this is making something go down the tree because it'll be less important. So again, this has a bunch of names: bubble down, percolate down, sift down, so on. The Zybooks uses the concept of percolate, either up or down, for both of these. A very common term for this process is heapify. That's used in the Corman text, and our lab will use the term heapify. The Java priority queue, again, uses the term sift up and down. Okay, so those are kind of internal operations that are needed to maintain the order property of the heap. And oftentimes that while loop that we looked at will be broken out into a separate function, separate method, so it can be used for these two different reasons: for dealing with adding data and increasing the priority. Those are two separate things. And also the idea of removing data or decreasing the priority. In both of these cases, this idea of moving a node up or down is usually separated out and used as a part of the insert process, but it could also be used elsewhere. So to make the code reusable, those loops are kind of broken out into their own separate piece. Okay, to be able to change the priority of an item that's already in the priority queue, to be able to kind of adapt an existing item's priority, we need some approaches to do that. So if we want to increase the node's priority to make it more important, which may make it move up in the heap, with max heaps, which Wikipedia and the Corman book use, you refer to this as, they both refer to this as increasing the key. In our case, we're doing a min heap, so we're going to have a decrease object that has a decrease method. So this is the second thing that we'll have named decrease. So there's the decrease of the heap itself, which is about moving an item up in the heap because it's becoming more important. And there's the ability to decrease something in the heap's priority, to actually change the priority of something in the heap. And that is a method called decrease of the decrease object. The Zybook and Java priority queue don't really describe this idea of changing an existing item's priority. You can also have the complementary notion of decreasing a node's priority. So Wikipedia is the only of these sources that actually addresses that. And since it's a max heap, it refers to it as decreasing the key, which will make it less important and move it down the heap. So this is so confusing. So just kind of a basic summary of really the big takeaways here. Heap can mean different things. It can be a binary heap, which is what we are talking about in this class. It is this tree-shaped thing that has both a shape property and an order property. And most of our lab is focused on maintaining these things. There are also other data structures referred to as heaps that have roughly the same sort of goal in mind and support the same sort of abstract operations. They just do it in slightly different ways. There's also this concept of the heap memory. Okay, so big takeaway here for the lab, basic summary. There are several concepts and the lab uses terms for those specific concepts. Adding more data is insert. Getting the best item is going to be handled by the extract min. Enforcing the order property after adding data or increasing a priority of an existing item will somehow be handled by a method called decrease. Enforcing the order property after removing data or a decreasing priority would be done with heapify. In this lab, you don't have to worry about allowing the priority of an existing item to decrease. You do have to support being able to increase priorities. So this was kind of be like the analogy earlier of someone in the emergency room who takes a turn for the worse and they need to possibly move up in line to get immediate treatment. Okay, so with that, this is the focus for the lab. One last thing to mention. So there is an approach to transforming an existing array into a heap. So if you happen to have already have an array filled with data, or actually almost any sort of binary tree, there's a way to start at the back of the array and slowly transform it into a heap, kind of working up from the last parts of the representation of the heap upward. So the basic idea is you kind of start with the leaf nodes and slowly build your tree upward from the back of the heap upwards. Okay, the reason I mention this is because it is a little bit better than the approach we've talked about. So this bottom-up approach is referred to in the Corman text as the max heapify. They provide the full pseudocode for it. It can be found elsewhere. And the time complexity is slightly better than what we've talked about so far. It's order n time complexity.